Welcome to another Ultralight Airplane Design video from the Ultralight Airplane Workshop. Now when I say ultralight, I'm talking about ultralight as defined by Part 103 of the United States FAA regulations. This video is part of a series of videos covering the UWS-4 Ultralight Airplane Design. And we're now on Part 11B. Now Part 11 is covering aerodynamic loads on the airplane, and specifically span loads, so loads along the span, and chordwise loads. Now 11B is going to be covering load distribution along the span, which is similar to what we did in the last video, but we're specifically covering how that span load changes when we deploy flaps and when we move our ailerons. And if you looked at the end of the last video, you'll notice that this is a slight difference from what I said we were going to do. I said we were going to work on the shear and bending load of the spar of the airplane. But when I started to get into that video, I realized I really need to talk a little bit more about these other span loads, since we just did span loads in the last video, and if you watch that, it'll still be fresh in your mind. So it's probably good to talk about these alternate spans that we need to talk about. And then in the next video, which will be 11C, then we'll start to get into the bending load and the shear load on the main spar of the wing of the airplane. In most of our videos up until Part 11, we had been using Dan Raymer's book, Simplified Airplane Design for Homebuilders. But when we got into these distributed loads, that's something that Dan does not cover, and he recommends using Part 23 of the FAA regulations, and that's what we're going to be doing. Although we're going to be using an older version of Part 23, since Part 23 now has the guts of it removed, and those guts, those details, have been moved over to an organization called ASTM, and you have to pay in order to get that information now. I'm going to use an older version of Part 23, which still had that information in it, and that's going to be Part 23 prior to 2018. Let's get to it. Oh, before we actually get to it, let's back up a second. I want to thank my Patreons on Patreon. You guys have been fantastic. You've been supporting the channel. I really appreciate it. And you guys are what's keeping the channel going. Thanks a lot. Now, a quick review of what we talked about in the last video. Again, we were talking about Spanwise load distribution, and let's go to this next picture. So we're talking about how the load on the airplane's wings is distributed across the span, and that's this yellow line here. So the higher this line is from right here, the more lift we're getting. In this case, a Spanwise load distribution is going to be pounds per foot, so that per foot is span. In this video, we're going to talk more about how flaps and ailerons affect that span load distribution. But in that previous video, we used two ways to come up with it. One was with an estimation method that Chris Hines used in his book, Flying on Your Own Wings. Now, it's very conservative. In other words, it overestimates the load out on the wingtips, which puts more bending moment on your spar. And then we used OpenVSP with its aerodynamic analysis, VSP Aero. Well, in this video, we're going to continue using VSP Aero. So here's part of what prompted this video, kind of a continuation of the 11A video. Here is our flight envelope for our airplane. We've talked about that in a previous video. I'll put a link to it up here in the upper right-hand corner. Now, in a video 11A, we really only talked about operating here at this point A, condition A, which is our maneuvering speed, 55.7 knots. Where we'll stall before we damage the airplane. We did not consider any of these other operating conditions. D, which is at the same N1, which is the same load factor of 3.8, but at our dive speed, our design dive speed, V sub D, and also here at our negative 1.52, this is condition E, still at the dive speed, and then we have this condition G, where we'll stall the airplane negatively before we'll damage the wings, but still at this N sub 2 of 1.52. And in addition, we need to look at our span distribution at V sub F, which is our maximum design speed with the flaps deployed. We also need to look at this stall speed. By the way, the load factor is 2, N sub F, right in here. So we need to look at these regions, and in addition, deflecting our flaps when our load factor is 1 at certain speeds. Actually, there's another condition where we're operating at 2/3 of N1. We'll get to that. So first, let's explore these conditions at A, D, E, and G. And so I've outlined those conditions over here. Our load factor of 3.8 at V sub A, 55.7 knots, that's condition A. And we talked about in part 11A, like I said. And then these other three conditions. So N1 at V sub D, N2 at V sub D, and N2 at stall, right here at G. So I've calculated out some of our conditions. So using a load factor, our maximum gross weight, this is the load condition we'll have. Here is Q, our dynamic pressure. And when we do some calculations, we figure out our wing has to have a coefficient lift of roughly 1/2 out here at this condition. Now using OpenVSP, I did that interpolation like we talked about in 11A to figure out what angle of attack we need in order to get this coefficient of lift. And that was very close to 1 degree. And then I did the same sort of things down here. So N2 is minus 1.52. V sub D, our design dive speed is 95.3 knots. So our coefficient lift there is negative 0.2. And then down here at condition G, our coefficient lift is a negative 1. And again, there the angle of attack is minus 25.6. So let's take a look at this spanwise load distribution for all four of these conditions and see how they differ. So let's work on our N1 condition up here on this red and blue line. So that's going to be conditions A and D. And you can see the legend here. So the blue line is condition A, the red line is condition D. So this is our design speed, this is our maneuvering speed. And so you can see, at least right out in this area here, they overlap each other very well. And in fact, here in the middle area, they pretty much overlap each other, except there's just a slight bit more in the condition D. So the design speed has just a fraction a bit more lift here in the middle. Not enough to really make any significant difference. But out here from about, halfway out on the aileron on out to the tip, you can see they diverge quite a bit. So the condition D design speed has a less of a dip where that wingtip starts, where we have that big dihedral change. Now if you average it out, it looks like, I believe that the red line, the condition D, might give us less bending moment than the condition A. I will do a bending moment calculation to see if there's much difference, but I don't think there's going to be much difference. I still think that condition A will have a little bit more bending moment, so it's probably the one that we should use in designing our spar. But I will do that calculation here when we do that next video. But what about in the negative direction? Okay, we have condition E, which is the dive speed, condition G, which is that stall speed. They're very, very close to each other, pretty much that whole distance. Just hardly not worth talking about the difference between those two. Now for us, since we're using aluminum, this negative one, at least as far as the spar goes, probably will not be a factor. Since our compression and tension loads in our aluminum are fairly close together, that means the spar caps will probably be pretty much the same exact design on the top and the bottom. Because in this condition, the top spar cap is compression, bottom spar cap is in tension. If we had spar caps which had a significant difference in compression and tension, for example, let's say in tension, the material that we used in the beam spar cap was way, way stronger than in compression. In that case, when we are designing our spar, since the compression is pretty weak, we would have to make that spar cap pretty thick. And since in tension our material is fairly strong, we could make that spar cap fairly thin. And we don't want to make them any bigger than we need to because we want to have a fairly lightweight spar. But what if we turn it upside down and we're doing the negative G's, the N2 condition? Now with our airplane upside down, what used to be the thick side is now on the bottom, and it's no longer in compression, it's in tension. And the side that was on the bottom now on top, and it was that thin side because it was strong in tension, but unfortunately now it's in compression. And if you remember, our material is weak in compression, so now we had the possibility of this being too small a cross-section area to handle the compression load. So in this case, we may have to look at our N2 numbers down here, and if in compression this load is too much, then we'll actually have to increase the thickness of this spar cap in order to handle that N2 condition. Now that means it'll be over-designed when we're flying upright in attention, but that's just the way it is. I know I didn't explain that very well, but we'll talk about more when we start working on the moment of the spars. So these conditions up here are without flaps being deployed and without ailerons being used. Let's start talking about those conditions. Now I'm going to use some of the information from Part 23 at the FAA regulations, and specifically 23.345. Now one thing to remember is when we're talking about the force on a flap, it's going to be normal to the chord line of the flap, not necessarily normal to the chord line of the rest of the wing. And then normal basically means perpendicular to the chord line. Now our flaps on the UWS-4, we're talking about deflecting a maximum of 40 degrees. You really don't get much more lift when you go more than 40 degrees, at least not on the kind of flaps we're talking about using. You might get just a little more drag, but you'll get almost no more lift, so I'm not going to go past 40 degrees on deflecting the flaps. And that V sub F speed is 44.3. Let's go look at that diagram again. So right here, V sub F is at 44.3 knots. Now the N sub F, the load factor on our wing, on our flaps, is 2 at V sub F. So that's one condition we're going to talk about. The other one is the same load factor, but at the stall speed at 35 knots. And that is right here where we stall before we actually do any damage to the airplane. And specifically, in this case, we're talking about stalling before we damage the flaps themselves. So again, just like we did up before, I figured out what the load factor was, what the dynamic pressure was, and what the coefficient of the lift of the wing needs to be. I then used VSP Aero with the flaps deployed and figured out what that angle of attack I need in order to get the correct coefficient lift. And then of course, same thing here. So let's take a look at that. Condition A is that one we were just looking at up above, the one that we did in the last video, just for comparison. So here's that lift distribution. And then here is lift distribution with the flaps deployed at our load factor of 2. Now the red one is our lift distribution when we're stalling before we damage the airplane. This kind of greenish one is at the speed of V sub F. So you can see there's actually, it's fairly significant difference here between these two. So on this red one, we're flying at a higher angle of attack. In fact, let's look at that. So right here, we're flying at 20.8 degrees as opposed to 1.5 degrees. So 20.8 degrees, you can see out here, the lift out on this wingtip is quite a bit higher than when we're going much faster and we don't have as high an angle of attack. So that reduces the load out here on the wingtip. But you can see it transfers that load out here to the middle. So which one of these should we use in designing our flaps? We don't have to worry about it for designing our wing, the spar of the wing, because this one up here is so much greater than either one of these. The spar load will be designed for this condition up here. But down here, we need to start thinking about the flaps themselves. The flap being able to handle that aerodynamic load, and the attachment points attaching it to the wing has to be able to handle the aerodynamic load. The inner flaps, this is the center of the span here. The inner flaps come out to this point here, and this is where the booms are. And then the outer flap comes out to right here, roughly where this cross point is, right in here. So as you can see, we have more load in this condition on the flap area of the wing. So we would ignore this one, the red one, which is at stall. With what we've looked at so far, this V sub F at NF is what we need to worry about. Let's continue looking at some of Part 23. So there's two more conditions we're going to look at here. Now there's even more we really need to worry about. But for now, in this video, we're only going to talk about two more flap conditions. One is when we have a head-on gust of 25 knots, plus the effects of the propeller slipstream when we're at 75% of our maximum power. The other one is the slipstream by itself when we're at full takeoff power. But before we do that, let's take a quick look at OpenVSP on where the propeller is on our airplane. Here we are looking at the rear of the UWS-4. This blue area here is the disc of the propeller I'm thinking of using at least for the initial testing, which is the Ultraprop 1, and it's 59 inches in diameter. Now I designed the airplane so I could take a bigger prop up to about 70 inches, 72 inches, and so that that slipstream of the prop would not impinge any on the tail of the airplane. And it would come down here just a little bit lower, about to where the bottom of the flaps would be when they're deployed. So the back edge of the wing is pretty close to the bottom right here. So this prop disc does not quite go down to the bottom edge of the wing. And you can see that none of it impinges on the tail, and it's going to be sucking air from around this pod and help keeping it attached to the pod and maybe attached to the wing. Although when the flaps are deflected, it won't do that. So you can see that none of the slipstream impacts the flaps at all. And you can see it's actually behind the flaps by quite a bit too. So the propeller slipstream does not have any effect on us. So I'm not going to bother with this condition out here. And I'm pretty much going to ignore the propeller slipstream up here. So what I'm really only concerned about is what happens with the head-on gust at 25 knots. Now there are two conditions that I'm going to also ignore for now. That is gusts that happen in the more vertical direction. I'll deal with those at a later time. This 25 knot gust head-on is really significant, so that's what we're going to deal with here. So again, that is with our speed at V sub F, but N is 1, a load factor of 1 instead of load factor of 2. If you do this at a load factor of 2 at 25 knots, the numbers are just outrageous and make no sense. So we're going to do load factor of 1, which is basically a stabilized flight at our maximum design flap speed. And again, I went and figured out what the lift is going to be, what our coefficient of lift is going to be, what our dynamic pressure is going to be. And by the way, dynamic pressure is with the 25 knots added to V sub F. And by looking at this lift, you can see that it's kind of interesting. When we're at a stabilized flight of N equals 1 at V sub F, our load would be 517 pounds, load factor of 1. But when this head-on gust hits straight head-on, it increases our dynamic pressure a lot. So our dynamic pressure would have been 6.64. So here's our V sub F condition we did before, and our dynamic pressure was 6.64. But when you add in that 25 knots, our dynamic pressure increases by roughly 10 to 16.26. Well, by increasing that dynamic pressure, we're increasing our lift a lot. So we more than double our lift up to 1,265 pounds. So that basically changes our load factor from 1 to 2.44. And that's going to change the lift and the span load on our wing a lot. So let's take a look at that. Okay, so this kind of purplish line is with our gust head-on load factor. So you can see that our original ones down here are way below what this new one is right up in here. So now, instead of this kind of greenish line being the maximum force we need to think about on our flaps, it's now this one. This is a lot more force on our flaps that we need to be able to handle. But it's still below our condition A for our wings, so it's not going to affect the spar on the wing, just the flaps and their attachment mechanisms to the wing. I put a few bullet items in here that we're really not going to consider in this video. I thought I'd go ahead and mention them though. At some point when we're working on how we're attaching the spar of our wing to our fuselage, well, actually and to the booms too, we need to take into account an asymmetric condition where we have 100% of our load in that condition A, but only 70% of our load, or 75%, on the other wing. So that's going to create an asymmetric load there at the fuselage that we need to be able to handle. But we're not going to worry about that in this video, but I did want to mention it. So now we're going to talk about other asymmetric loads, which is the ailerons. And by the way, you can find this stuff in part 23.349. So there's two conditions we're really interested in for the most part. There's one condition where we are flying at 2/3 of N1 at our maneuvering speed, and another condition where we're flying at 2/3 of N1 at our dive speed. Now, on the first one, we're worried about what's going to happen to our spanwise loads at full deflection. On the second one, at our design speeds, we're only worried about what happens when we deflect our ailerons 1/3 of the deflection. So again, I went through OpenVSP and figured out what our coefficient of lift would be for 2/3 of condition A, and figured out what that angle of attack was, and then did it for 2/3 of condition D, and figured out, again, coefficient of lift of the wing, and that corresponding angle of attack. And then lastly, there's a requirement that talks about handling a sudden maximum displacement. Now, on these two up here, they were more concerned about roll rates. Well, we're not going to worry about that, but they were more concerned about roll rates. Here, we're talking about a sudden displacement where the inertia of the booms and fuselage of the wing are going to try to prevent it from rotating, at least initially. And so that'll put an interesting load on that wing. and we're going to deal with that condition too. So let's take a look at those. So here are those load distributions. Now I didn't put the condition A on here. If you remember right, that's about 100 pounds per foot up here in the fuselage area. So that condition A is still going to be more than just about all of this. So what we're worried about here is not the spar loading, but the loading that we're going to have on our ailerons. Now, just for comparison purpose, I put these green and blue lines in here are with the ailerons not deflected. So at 2/3 of our A condition and 2/3 of our D condition. So that's these two here. And then these other two are with the ailerons deflected. So here we have more lift, so this aileron is deflected down. Here we have less lift, so this aileron is deflected up. So one that's given us the most force on our aileron goes from about here out to right here where this dip is, where the wingtip starts. So you can see it's this purple one that gives us the most force on the wing, and that is the one at condition D with the aileron deflected just 1/3 of its travel. And it looks like over here on the other side, the one is giving us the most downward force, giving us the least amount of lift on this side is again the purple one. So again, that's our condition D up here at, whoops, I didn't quite get this. This should have been 2/3 in one, just like here. So condition D, 1/3 of the aileron deflected gives us the most force. So we're going to have to design our aileron to handle this purple condition here. Actually, I shouldn't say that. There's one more thing we're going to have to take into account, and that's going to be the chordwise distribution. When our wing is at a high angle of attack, generally the load is going to be moved more toward the leading edge and less on the trailing edge. And when we're in more of a flat condition, it's going to be moved back more towards the aileron. But that then means that this purple one should still be our worst case scenario. But what I'll do is I'm going to use these distributions later and include them in chordwise distribution to figure out what that maximum load is going to be on flaps and ailerons. So this is just getting the spanwise part. We really still need to look at the chordwise distribution to be positive that we have the correct maximum loading on our control surfaces. So we still have a little more work to do. And then last thing to look at is this maximum sudden displacement. And again, that's with our load factor of 1, but at our maneuvering speed. So take a quick look at that. So that's this condition here, this blue line. So this green line, again, is our condition A. So you can see our flat area is close to 100 pounds per foot. This blue line is the condition where we were testing our ailerons, but with the ailerons not deflected, because I wanted to give a comparison of deflected versus not deflected, so you can see what that looks like. So in here, we actually have finally some negative lift. You can see it's going below 0 right out here. So that maximum lift there is, about 45 it looks like. Let's go look at our previous, and now we're up to about 80. So it looks like this condition really isn't much of a factor for us, at least as far as load on the aileron goes. We will want to take a quick look at how that asymmetric load is going to affect our connection to our booms and our ailerons, though. We'll check that out. So this last chart here is basically a repeat of what I did in the last video, saying that we're going to work on the wing shear and moment calculation so we could work on our spar of the wing. But this time, I'm pretty sure we will do it. I don't think there's going to be anything else to stop us. Well guys, thanks for watching. Until next time. A user named Want to Build on the Ultralight Airplane Workshop's Discord server suggested that I should wear a crown with some jewels on it for some videos. Well, this is as close as I'm going to get. Enjoy. Later.